I just made you co-host, Albert. I don't know if that allows you to share your video if you want. You can see your screen. Yep, I can see your video now. Nice.
I'll remain visible for a little bit and then I'll switch it off.
Okay, sounds good.
Yes. It's actually, it's a lady's sweater. I had to find someone, which I mean is absurd how large it is, but to find something suitably tacky was only in the ladies section. Otherwise, the men's sweaters were trying to be too cool.
Makes sense. All right, well, I'm going to get started then. Thanks everyone for attending. My name is Drew Buchanan. You may know me. I'm the engineering manager here at True Insight. Really excited to have a guest presenter today for PSIM. I'm going to introduce the presenter as Albert. Legacy PSIM guy, works directly for Altair. Really excited to be here. So with that, Albert, I'm going to hand it over to you.
Sounds good. Thank you so much. Yes, as was mentioned, Altair acquired PSIM, the company that I worked for 9 years, called PSIM, which was a development company for PSIM, in March of this year. And that has really, I think, been quite exciting. There's a poll webinar that just popped up. I don't know if folks want to quickly punch an answer in there for that. But yeah, we were acquired, and really there's been some exciting things that have been happening over the last few months as we integrate into the Altair ecosystem of other simulation tools. So a basic overview here is intro PSIM a little bit if you're not familiar with it. We'll talk over some integration of PSIM with the existing Altair solutions. Namely some MotionSolve stuff for multibody dynamics. And then we'll also poke into some Flux co-simulations. And then there is we'll get into some other topics that I'm excited by these days, which is connected EMI, some switch models. We'll get into some power supply basics, and if time permits, embedded code gen. I had been planning to talk about not so much about the MotionSolve and the Flux things, but those are recent developments which will be kind of exciting and will be included in the new release of PSIM, which is slated. Oh gosh, Drew, do you know when 2022.2 is supposed to be released? What the release cycle is there? But for HyperWorks, it should be next week, maybe.
I think so. Yeah, next week.
Yeah, next week. Yeah. So the new release cycle of refreshing PSIM and Flux Motor is all happening next week. So yeah, some of this, you should be able to do everything I'm doing next week to put some pressure on the development side. So that will be exciting. I think it looks to me like there's a lot of automotive people in the in the slides today, in the session today, so that this is right up their alley. Okay, so yeah, we'll slip by this one about PSIM. So PSIM was first developed about 27 years ago. It was specifically developed for the simulation of power electronics, and you can see it positioned here between what we would call the system simulators, so Simulink, Activate, maybe ANSYS Twin Builder might fall into this category too. And then the device level simulators like SPICE. So PSIM occupies this nice little zone here in between the two of them. You can do control level simulations with PSIM. You can do device level simulations with PSIM. Obviously, there's stuff that SPICE does well, which is the selection of circuit models that and IC models that get presented, and then clearly Simulink and Activate have functionality beyond what PSIM provides. I think of imaging processing toolboxes and things like that, which is just not power converter related. So why does PSIM exist? It's widely regarded for simulation speed, robustness of results, and obviously, so that lends to robustness and convergence, dependable convergence. Okay, the PSIM advantage. So PSIM was originally developed due to in the 90s, because power converters and power electronics were becoming more prevalent and more commercially or industrially relevant as more devices were being available, more switching devices. The tools used at the time to simulate power converters were things like SPICE-based tools and things like Simulink, which were not specifically made for the simulation of power electronics. What is unique about power electronics? Well, it's the derivative. When we introduce a switch transition. So when we turn a device on or off, that introduces a derivative, which needs to be solved. So Simulink or other tools like that, they are not set up to deal with this sudden change in the voltages and currents. And when there's lots of changes, say multiple switches introducing these things can go for a bit of a ride. So yeah, PSIM was specifically developed to deal with to be as robust as possible, solving and simulating these derivative or these switching events. And that's really the name of the game with what a purpose-built power electronic simulation tool is meant for. It's to deal with these switching transitions because they can cause issues with other solved algorithms. Here's a quote from Kevin Lee from Eaton. Highly valuable tool. He uses it to study all aspects of the motor drive. We're going to look at some interesting motor drive simulations in a moment. Okay, so I want to spend a little bit of time talking about motor drives. We'll talk about power supplies a little bit later on, but based on some of the stuff that has recently gone on with development, linking to Flux and things of that nature, the motor drive part shows some really interesting things to discuss. And this is where things can play, and this could be a general slide as well that's specific to motor drives right now, but a lot of what is here can also be moved over to regular power converters, be it a consumer grade converter or something, a grid link PV application. The only thing that really would be crossed is the MotionSolve for the mechanical load or the Flux motor for the motor aspect. But this is also gives you a look at where things are going with simulation, with PSIM as it integrates into the existing Altair tools, which are all mentioned here. So so focusing on a motor drive, the MotionSolve will show you some interesting things with MotionSolve in a second. So this is a multibody dynamics tool. So we can include a simulation of the motor drive combined with the multibody dynamics. Flux and Flux motor are tools from Altair for FEA of motors for low frequency electromagnetics. What we're going to talk about there is we're going to see what can be learned when we include a Flux or Flux motor model into a motor drive simulation. And then FECO is a high frequency electromagnetics tool. The fun thing about PSIM is that because we've been set up to deal with derivative robustness in the power converters, we also are able to deal with high frequency interactions in distributed cable models that can typically cause issues, especially if you use a state-space matrix approach, which can lead to stiff matrix equations. So I'll show you a little bit later what can be learned when we include cable models into simulations of power converters and how that can promote interaction between the converter itself and its power source or its load, and also how that plays into maybe radiated or conductive emissions from the cables or from in that space. Pollux PCB and FluxPEC, these are tools that can be used to calculate parasitics of a mechanical structure, say a PCB or say bus bars, and these play into the conductive EMI side of things. SimLab is another fun thing where we can take losses from a PSIM simulation on the devices and bring that up to a 3D CAD solve. So we can look at that. So that's SimLab. I don't have any demos of SimLab today, but this is we're working on these right now. We're building an Altair inverter where we have an inverter, and then we develop the losses for it, and then we solve it in 3D time and look for 3D space and look for a thermal steady state. We'll do the same thing with a little Altair phone, so we can look at the heating inside due to the power converters. So that's going to be, I'll show you how that will play forward when we get there. There's the control side as well, which is, activate, embed, and PSIM all can do control simulations. PSIM and embed both have code generation workflows. And there's some things there to talk about too. Moving along here. Okay, so power hardware. These are all the things that deal with power hardware. I don't want to spend too much time on these. These are all kind of control design related tools. And then here's some system level simulation tools to talk about. So again, as PSIM matures inside of the Altair world, you'll see more and more links with other tools. Other tools to come up will be things like a hyperstudy, so an AI-based tools to help direct simulations to learn things in an automated way with greater scripting and all that kind of fun stuff. So there's lots of other things to come. These are sort of the things that we've been dealing with just recently. So a main strength of PSIM is simulation complexity. I just want to know if there's questions. Okay, there's the chat. Okay. And if there's questions, I have my eye on the chat now. So just type in a question and I'll see if I can answer it. So there's the simulation complexity aspect. So PSIM as a tool features a high degree of complexity abstraction. What we really want to be able to provide end users is to be able to use a particular model type or functionality abstraction to help you have the best convergence, the best simulation times, and the right amount of information for your needs. So if we talk about switch models, ideal switch models versus non-ideal switch models, thermal in the middle. We talk about machine models, ideal spatial harmonics, frequency parasitics, nonlinear FEA co-simulations. There's lots of things here, and we'll run some simulations where we can see the differences here on different machine models and how those play together. Connections, so ideal wires, so just point-to-point bus bar or a single RL value or distributed cable model. Again, the range of availability there is up to you. And then obviously gate drives, again, another example of basically an ideal on-off source versus simple voltage sources or full-on switching models of gating drive supplies and circuits. Okay, so this is the developed torque of a motor drive, and we'll run some simulations and look at it in a moment. But what I want to highlight here is there are 4 different simulations here, and I've used 2 different models. I've used the co-simulation with Flux motor, and I've used the co-simulation with Flux. Now, the yellow line in the middle here, and we'll look at some simulations in a moment where we actually see this. I'll just talk about a couple of slides here, and then we'll flip out of here and look at simulations. So the yellow line here is the Flux motor model. So this is a non-ideal LD and LQ. And you can see that the ripple there is quite minimal compared to the red, the blue, and the green lines. This is spatial harmonics that we're looking at here. So the red line, if you look at the peak-to-peak values, the red line is the smallest, and that is an ideal switch, so no conduction loss and no dead time. The blue line shows us what happens when we incorporate 2 microseconds of dead time with an ideal switch. The green line is showing us the impact of a dynamic voltage drop on the conduction of the devices. So right away, we're seeing a change in spatial harmonics torque ripple in a motor drive as a result of changing the fidelity of the switching model that we're using. And then we also see a changing fidelity in the developed torque based on the type of motor model that we're using. So this is new stuff. So these models were developed, we started doing these simulations maybe a couple of weeks ago, and this is going to be built in included into the next release of PSIM and Flux, which is, as Drew says, next week. And so here's another really fun simulation. This deals with motion multibody dynamics. So in this particular simulation, we have a motorcycle. And the drive for this motorcycle is a PSIM motor drive simulation, okay? And what we can look at here is what happens when we, so that we need to be, you know, it's one thing to run a motor drive with a constant torque load. It's another thing, and we'll look at these things in I just want to get through a couple slides and we'll pull up some simulations to kind of look at this in a bit more detail. It's one thing to do a motor drive simulation where we have ideal motor with no spatial harmonics and no LDLQ changes. When we add spatial harmonics and we add a changing LDLQ, that changes the control response of the motor. It introduces more, it makes the controllers work harder, introduces more noise into it. So what we can see here is that we originally had an aggressive motor control, which was stable with an ideal machine, and even was stable in a constant acceleration use case. But what we see is what we can do here is we can see what happens when we add in now a multi-body dynamics of the system. So what we're seeing as this kind of plays over and over again is the top one is we've tuned the motor. So the bottom one was the original, which was an aggressive control loops for ID and IQ. And we can see, don't think about it, just replay the video. Oh geez. Drew, I'm not, it's just my PowerPoint that's frozen, right? I haven't frozen, just to be sure.
Okay, no problem.
No. Am I frozen or is it just the PowerPoint?
It's just the PowerPoint.
Okay. Close. I'll replay that video. Thank you, Microsoft PowerPoint, for your contribution today. PowerPoint. We'll come back to that. We were here. Okay, so the bottom one was giving us a good, and you can see here, so the bottom, this is developed torque, and this is the throttle command down here, and this is the tire slip of the two systems. So the red one is the aggressive controller, which was looking okay during acceleration, but then what happened is that the friction coefficient changes and caused the traction control to kick in. And so you can see with the less aggressive motor control algorithm, this is for the current loops, for ID and IQ, it was able to handle the changing traction requirements. And you can see how that changed with the tire slip. But then what we see is the, and as we see here, so the top one was able to maintain traction and still recover, where the bottom one went out of whack and caused our dear little friend to crash. So this is a full like motion multibody dynamic simulation that we did using that. And again, it looked okay with an ideal motor model, but when we went to the non-ideal model, it really started to show issues. So here's a little look at that. So we did an ideal machine, and then we did the same controller with the non-ideal Flux SIM, which had the spatial harmonics and the non-ideal LDLQ, and we can see the instability in the control response, right? It's still got up to steady state speed and it's still recovered, but we can see that there's oscillation there in the ID and IQ values, which was causing oscillations in LD and causing oscillations in the developed torque. So it was marginally stable, but it still got up to set point speed. And we can see that none of that drama was present in the ideal motor model. So in this case, there's two control scenarios. So we're switching at 20 kilohertz. Then the inner current loop had a 2 kilohertz bandwidth and then a 250 hertz bandwidth. So we did a 10x reduction there. And we can see that, and we did the ideal and the non-ideal. And you can see right away that the non-ideal motor model really behaved a lot differently with that more aggressive controller. And here's another slide looking at how we can introduce these we can use these co-simulations to look a little bit more here. So This is again with the motor model from Flux, which gives us copper, core, eddy, and hysteresis losses. We also are using a thermal model here where we can change between space vector PWM and DPWM and look at how the losses change on the device itself. So we can see the developed torque is roughly comparable. It, on average, is the same. Our total losses from the inverter were reduced by about 300 watts, and that's mostly in the switching losses. Then we see the copper losses, the core losses, and eddy losses are different. So copper loss reduced by about 90 watts, and the hysteresis losses went up by about 10 watts with DPWM. So DPWM saved us about 380 watts at this operating point. Okay, and we've modeled loss, conduction loss, and dead time modeled with IGBTs here. So let's, what's my next slide? Yeah, so let's scoot out of here and let's look at a couple simulations. Are there any questions while I'm heading over to simulations? Okay, perfect. Okay, so if you're not familiar with our design suite, this is it. So this is the motor control design suite, and what it allows us to do is to have a motor drive simulation and then tune it to our operating scenario. So DC bus voltage, switching speed, a constant torque load here, you know, some motor parameters, some basic motor parameters, and the motor control parameters here too. So we can basically click update parameter file, and it gives us some controllers for us. It gives us a speed torque curve. So this is our operating envelope, what's possible based on our DC bus voltage. So if I come in here and say this was a battery pack and we were at low state of charge, so say 400 volts, we can generate a new speed torque curve. There's the power curve, torque curve. So there's the new torque curve versus the old torque curve. And we can see, say, 8,000 RPM, 200 Newton meters versus now 150. At 4,000, we're just above 200, whereas here we were above 400 Newton meters. And then the max torque region is about halved as well. You can really see it in the power profiles. So these are peaking out around 120 Newton watts versus 200 is watts, and 150 versus just under 100 watts steady state. So these are some interesting. So this is one thing you can do with it. And the other thing you can do with it, again, you can generate these control loops. So this was with an ideal model. And again, we can run the simulation and we can see the shaft speed. We can see the developed torque. Here's the developed torque of the machine. And again, it's the control that values here, ID and IQ. So we can see what this looks like. So this all looks pretty good. And, you know, one of the things you could do would be then to take this away and then link this to MotionSolve to do that multi-body dynamics that we looked at a bit earlier, right? We can also, so what has happened is we've now got the ability to do the Flux motor lookup. We've also got the ability to do the Flux itself lookup. So Altair has two tools. There's a tool called Flux Motor, which is basically for designing more common motors in a more of a template kind of way versus Flux, which is a full 2D or 3D solve of your motor itself. And so how we're doing this right now is it's based on lookup tables. So the lookup tables are generated by Flux, and they include a lot of information. So we can pull up what the information looks like here. Okay, so these are some losses. Let me pull up. Flux. Here's the lookup table. Let me show you the data set that's being used here. Okay, so we've got rotor position, we've got D and Q flux, we've got iron losses, we've got a core, we've got hysteresis, all that kind of information there. LD and LQ as dynamic and static lookup tables. So it's really a fairly comprehensive listing of lookup values and information here. So this is the motor model, and again, it's a lookup table. But from there, we can look at this kind of information. So here's the losses from that machine. Here's what LD and LQ look like. The developed torque. Is there, and we're able to zoom in and see just what exactly is going on. So here's what the LD and LQ values are. Here's the developed torque of the machine. And again, this is an ideal switch. So going from here is relatively straightforward. We can come in here, we can switch this to a thermal model. So this models our switching and conduction losses and gives us a first pass at our heatsink. We can also do, change up the DC bus, put in caps, all that kind of fun stuff. So from here, it's relatively straightforward to maybe move towards something like an efficiency plot diagram. If I come down to this slide, so generating an efficiency diagram of both the motor, the inverter, and the drive system at the range and the envelope of operating points. So this can be easily developed from that kind of that model that we were just looking at. And then this gives you a good idea. And you can generate these plots for different junction temperatures and different, if you're running off a battery, different battery states of charge. So you can do a nice drive cycle evaluation or that sort of thing. So these are some nice things that can work from there. So again, that's going to be next week that gets released. So coming away from the Flux models, we'll come back to some simulations. I just want to make sure I get through content here. Again, it comes back to your decision about what kind of model you're going to use, be it an ideal switch or the ideal machines or whichever you're going to use. And so it's really about, simulation complexity being your choice. Switching off this one. So this kind of covers the ideal switch, the thermal switch. So we've looked at the ideal switch. I haven't shown you a simulation yet with a thermal switch. We'll look at what the level 1 and level 2 switches can show us in a moment here. Bridges me to conductive EMI. So what we're trying to do with on the EMI front is show what can be learned in simulation versus discovery in chamber. We're not going to ever claim to be able to replicate 100% what the hardware will tell you. What we do want to be able to do is to give you actionable design decisions, so you can learn these things in simulation before you either pay for testing or build prototypes, or you can look at sensitivity to certain things. So it's these things that we want you to be able to understand. So again, looking at how we can best mitigate our EMI issues or filtering and things of that nature. Okay, so let's look at, so there was some work done at UT Dallas. They looked at a dual active bridge converter to look at conductive EMI. And we're going to be looking at the common mode current here. So this is the setup. So basically the dual active bridge with silicon carbide devices on the primary and secondary. These were the parasitics associated with it. Those, you can measure those, you can derive them like hand calculations. Some people do that a little bit by hand calculation, or you can use, you will be able to use in Q1 next year, Flux PEC or POLX PCB to be able to come up with what these parasitic values are. And then this leads you to be able to do these sorts of simulations. So I'm not going to say that we're going to, again, replicate hardware 100%. What we're trying to do here is provide you again with actionable design decisions. So in this case, we're comparing hardware versus simulation. Clearly, we're not showing you this very high frequency rippling here, but we are showing you the same trend and the same peaks and the same damping ratio of the major signal. And that's really what we care about. This is the common mode current. And importantly, this work was done. So this is the hardware, and this is simulation with PSIM. This simulation was also set up and run with a spice-based tool. I won't name it, but it took overnight to run, whereas the PSIM simulation ran in about 30 seconds. Here's some comparisons of hardware versus PSIM. The transformer was originally not modeled very well, so this spike here comes back to an issue in the transformer model. So again, we do need to have an understanding of what we're dealing with and be able to interpret results properly. We can't just, this is a fairly complex subject. So this is really, I think, the fun simulation, the fun slide to talk about when it comes to using PSIM to do these sorts of things. If you're not aware, PSIM has, and I'll show you an example right away, PSIM has the ability to run a simulation and then save that state, and then use that state as the starting point for another simulation. So in this case, we could run a base simulation that takes 100 milliseconds to get to steady state, and then maybe we only need 20 milliseconds to do our analysis of the EMI. So what we could maybe have to do, so we could run this first simulation with a fairly coarse time step, and then the subsequent simulations with a fairly small time step. So if you were to run one simulation by itself, maybe the base simulation would take half an hour, and the testing and the last 20 milliseconds would take 10 minutes. So you'd end up with like a 40-minute simulation. So if you were to do all four of them by themselves, it would be 160 minutes worth of simulation. But what PSIM can do is it can use this, we'll do the first simulation, and then all four of these simulations, we can script and we can run simulations in parallel so that we're running on open cores or open threads on our processor. So that allows us to run these four scenarios in not necessarily the time of one simulation. So if it was going to be 30 minutes here and 10 minutes for one, it would maybe be 30 minutes here and then 15 minutes for four. So we're able to do this branching and testing, which really allows us to discover sensitivity of these things in a very nice way. This is, I think, is a very powerful workflow. And let me just kind of show you what we're talking about here. So yeah, I'll use this simulation as the start. So what I can do is I can come in here and let me just put it back to nominal 650 volts, update parameter file. So what I'm going to do is I'm going to set the save flag. And I'm doing this manually just so you can see how it works. But this is how things would run if you were to do this in script. So you can write a script that'll automate all of this. And so we're going to run it and we're going to get to 250 milliseconds and we're going to have that save flag set. So we're going to run this. So this should be a fairly quick simulation. Excellent. And we got to our endpoint here, 200 milliseconds. Is it 200 milliseconds? Yeah, 250. Where's the last 50 milliseconds? Print step, total time. Where's the last little bit? Oh, okay. Anyways, so then what we'll do is we'll now toggle this to be 0. And I'll do the load flag now at 1. So I'm going to use that endpoint as the starting point for the next one. And we'll run another, say, 350 milliseconds. And let's change the reference here to be minus NMREF. And then we will rerun. Hopefully that changed signs. Excellent. So there's the next bit. So we were at 8,000 RPM. I changed the sign of the torque of the speed reference, and we ran the next chunk of simulation. And I could also then use that same starting point, and I could say have a different time step. So let's just drop that. It's 10 microseconds. Let's go to 5 microseconds. So I can change the time step. I can rerun. So I can do this sort of simulation, and you can automate this process. You can run it so that we have, again, the test scenarios coming from the script. You could have a spreadsheet of different test scenarios and run through each one. And so that's really, I think what the power is here is to be able to, again, the strength of simulation is that we're not going to be able to replicate the hardware results really well. But what we can do is do, and what's the point of matching maybe one set of hardware, because there's variability in the hardware. So if we can analyze our sensitivity to different common mode capacitance values, maybe our sensitivity to the gate drive resistor, which impacts our dV by dt, di by dt, we can really push through a lot of simulations and really understand a lot more about our converter doing these sorts of simulations that I'm talking about with the multi-threading and the scripting. Okay, cable modeling. So this is really fun. This is a really interesting subject for me. So I don't know if some of you have seen this slide before. If you've been around me I've been harping on this one for a little bit, but I've got some changes to this as well. So we have the choice here between an IGBT and a silicon carbide device. The usual criteria for changing between IGBT and silicon carbide is switching loss or losses in general. The IGBT, we can see it here, has this fairly long, it has a slower transition between on and off than the silicon carbide device right here. And why does that matter? Well, this will, can I show an example? Yeah, I'll try and show an example later. I'm just trying to get through a lot of different, the question is, can you show an example of using the EMI simulation using scripts? I will try to a bit later, but the EMI simulations take a little bit of time to run. The typical steady state values are in a few minutes, and I'm cognizant of time here. We'll see where we get to towards the end if I can pull one up. So IGBT versus carbide. So yeah, we can see that the slower transition means higher switching losses. There's more time that the current and voltage are overlapping to provide us with that pulse of area under the curve. So silicon carbide is attractive from that front. But what happens is now we've got a bigger dV by dt here, a di by dt as well, which then, if we remember the basics of inductance and capacitance, is that those impedances are functions of frequency. So let's see what happens with a little test scenario. So we're going to introduce that switching edge into a distributed cable model, both the same way, and then look at cable, no cable, IGBT versus silicon carbide are here. And it's a basic R load. And this cable is 50 nano and 50 nano henries and 50 nano ohms and 150 picofarads between the cables. Now, this cable model is one that I kind of just dreamed up with some values from like an alpha wire catalog. The real strength with FICO is that you simply provide it with the 3D CAD geometry, the cable type, the shielding type, and basically you draw it out in 3D space, and it will calculate what those cable parameters are for you. And we can put that and drop that into a PSIM simulation. I'll show you. I have an example of that. I'll show a little bit later. So here's the load side. I mean, the switch side when we do the simulation. So we can see that the over voltage, the higher ringing with a silicon carbide device, again, interacting with common mode capacitances, interacting with parasitic inductance. All these things are leading to a higher ring with the green and pink here versus the red and blue, which the IGBT. The real fun is at the load side, where we see a much greater interaction with and ringing with the cable. And so this could be a real issue. So if we come back to this simulation here, if this was our real power converter with this cable here, what have we done? What we really have done is that we've potentially, our original goal was to reduce the loss here. So P loss on the switches. Why is that drawing like that? I won't try and draw. Clear, erase all ink. So we were trying to reduce the losses on the switches. And so that has happened. But what has happened as a result is maybe we have to put a choke over here now, or maybe we need a more aggressive EMI filter over here. So really what you're doing is shifting losses away from the switches and putting it into passive elements to mitigate the EMI or other issues that you might be dealing with. So there could be a cable, as I'm showing in this discard ink. So as I'm showing in this original kind of overview slide, we could put cables between the inverter, or the power converter and load, or on the other side between the energy source. Again, we're agnostic to where that cable goes, or if there's multiple cables, or if it needs to be a distributed model. But the point is that we can run these simulations with those models in, and we can use these level 2 devices to provide a realistic dV by dt and di by dt to that cable. So yes, then we get to here. So what we have then is the ability to record or measure the current in each of the conductors in each of the sections of the cable. And then we can take that and bring it out to FICO, and we can do a cable radiation profile from it. Now, this is just a proof of concept set of images here, where we took a cable and then overlaid a piece of information onto it. So just there's not that many frequencies, and they're all kind of clumped over here because we were just kind of looking to see what we could do. And we're able to look at antenna pickup. So this is E field and H field here. And we can see the surface current, so this is the sort of thing that we can do with FICO. And this is the beginnings of being able to appreciate what the radiated emissions might be like from cables in, either say battery to our inverter, or if we had a cable between our motor, our inverter and our motor. So we can include this sort of thing here. Yeah, so this is, again, linking with FICO and PSIM. And let me kind of show you what that cable looks like. Oh, wrong one. No, sorry. FICO, those ones. FICO. No, okay. I thought it was this one, but it's not. It should be here. There it is. Okay, so here's that cable model itself. And this one was a individual conductors with a shield. So these are the conductors, and then this is the coupling to the shield. So here's the shields, and the only coupling between the conductors is through the shield here. And these are the kinds of values we're dealing with here for the R's and L's, so very, very small values. And then we build this up to look at cable test, to look at this sort of cable where we're grounding the shield and we've got the phases set up. So this was a basic simulation to test what was going on here. So this is a really fun simulation to work with. And we can do, we can look at, let's do a basic thing here. Let me disable this. So this is only got one voltage going, and we can look at the induced voltage on the other phases. Oh, it's finished. So there's the load currents. Here's making sure that everything was wired in. 2, 3, 1, 2, 3. Oh, and just to load it up. Sources, source ABC. Oh, it didn't have anything. Okay, I'm not gonna see. I've played with it last time I did it. I'm not gonna try and understand what I did wrong. But this is basically the gist of it. Each one of these is this cable, and we link it together, and then we can drop it into a simulation and run it from there. Okay, back to the slides. Okay, so some other things to talk about here is I was going to get into, so that's kind of a lot of the new stuff that I wanted to talk about. Now I'd like to talk a little bit about power supply simulation with PSIM, and then I'm hoping to get into some embedded code generation as well. So let's come back to here, minimize this. So let me just close everything down. Come up, okay, starting fresh. So while it's loading, I would also like to highlight the existing workflow with Activate. So this is one of the ways that you can link to MotionSolve. So basically a block has been added to Activate in the co-simulation library here with PSIM. And then this will link you out to, in this case, this is the radar dynamics model, where you can link between Modelica or MotionSolve blocks. This is the exact same workflow as the Simulink co-simulation. So we do still co-simulate with Simulink. That's not going anywhere. So you will be able to run a PSIM simulation of the power stage with Simulink driving the controls. And you will be able to use the Flux co-simulation there as well. So you will be able to drop that Flux model into your Simulink simulation, or if you have your controls in Activate or Simulink, you will be able to have that detailed of that power stage in PSIM. Okay, so this is the same workflow. Basically, you drop the block in, and the PSIM side, you can see the various labels that we have here connecting. So there's the inputs and outputs. So here's, say, the feedbacks, or the outputs of the voltages are there, and the currents are here as well. The RPM input is coming in. So we just put these little input and output nodes, and that which links us back out to the top level simulation. Okay, so close this. No, so that's, yeah, so that's how things are working, and the co-simulation isn't going anywhere with Simulink, and we'll just be further developed with Activate. But let's look at power supplies here for a moment. So you may or may not know about our resonant converter design suite. This is a really powerful tool for coming up with the control character for the resonant gate, the resonant circuit here. So we have this nice design curve tool that allows you to plot and look at the various inductance ratios and quality factor ratios and how they come back and play with the gain. So this is calculating now with a closed form solution, a range of, so here we see a range of, let me close this. So we see a range here of, and this starting point here of the gain is the 0 voltage switching beginning frequency normalized to 1 at resonance here. And we see the inductance ratio versus, so this is a different quality factor with a different inductance ratio. We can see how that plays in. So the strength of PSIM is that we're able to do a frequency sweep of almost anything. So what do I mean by that? Well, we can run this simulation, and we're able to look at what the output voltage is, VO. So there it is, there's the output voltage. 440 volts. And if we come over here, we're able to introduce a small perturbation into that frequency. So this is a relative frequency, K relative, I think is 0.75. So if I introduce a perturbation here, say 0.07, and we'll do it at, say, 500 hertz, wire that back in. we can see a perturbation in the, let's run for a little bit longer. Total time, let's do 10, and we'll do a little bit less on the perturbation. 5. There we go. And we'll pull up here, okay, relative. So this is our perturbation, and then this is our output voltage. So what we're able to do is we're able to, now this is a complex topology in terms of trying to figure out what the average model might be, is we can do a frequency sweep of this, and then that allows us to do a control design of this quite quickly, either the analog or current. So AC sweep elements, grab an AC sweep, find AC sweep probe, and then the AC sweep block itself. So basically how this works is we would use this to drive what our perturbation would be, and then we would measure the output voltage over here, and this would give us what the open loop transfer function looks like in a closed form method. And this is the basis of all of the frequency sweeps in PSIM, and this is a key aspect to control design. We don't care what this topology is. So in this case, this would be a resonant LLC. If you come in and look at some of our other examples, a complex topology to work with would be this phase shift full bridge, where there's 0 voltage switching here. There's an active secondary. We're doing peak thermal control, and we would be able to, again, the same kind of concept where we have a reference, and we can connect this in. Wire, and then let's drop in a perturbation again. We'll go at a kilohertz this time, and this is at 1.8, so 0.18. And again, we're able to look at that perturbation VO. So there's that perturbation forming, not quite at steady state versus the peak reference there. So this is the sort of thing. And again, we do those frequency sweeps where we can introduce that, and then we get our open loop transfer functions, and we can do control design from there. I wanted to touch briefly on the power supply stuff. I did overload this stuff with a lot of motor drive stuff because that was some of the really interesting things that were coming in the next release. Other questions? I see the time is at 10 minutes. I don't want to keep talking forever. I want to give time for some people to ask some questions. So if there are some questions here, please do ask them. No questions at all. Okay. So let's kind of talk a little bit about resources for you. So if you may be aware about, if we come back over here, AC Suite, if we click into help, there is always going to be, in some of these, there's going to be links to existing examples. There will be links to tutorial videos as well. So these tutorial videos, some of the links are maybe broken. And why are they broken? We should comment on what's happening on the other side here, is that eventually the PowerSim website will merge into Altair One. Altair One. So this is the support portal for all Altair products, and everything will migrate over here. Our YouTube channel, if you're familiar with the YouTube channel, PSIM YouTube, this used to be the PowerSim YouTube channel, but now it's a full Altair how-to channel. So this is now changeable. You see all the PSIM videos are here, but they're adding in a whole host of other videos for other products, Altair products. So this is now going to be the main resource. for where all the videos will live, and not just PSIM videos. So those are some things to look for that are coming soon. I will also comment that previously people used to send emails to support@PowerSim for support. That is going to be changing soon, and you'll be putting tickets through the Altair One portal. So you'll need to make an Altair One account at some point so that you can submit those tickets, because they'll in the old days with PowerSim, we just kind of answered the emails. In the new system, we need to actually track the emails and the close time and all that kind of stuff a little bit more closely. So please do make an account with Altair One at some point, and you will be able to then make tickets. And then there's also going to be a number of training sessions hosted next year. So I would like to share with you my training plan for next year. So the training plan is going to be 4 training sessions. Get started with PSIM training, 3 hours. You'll be learning all about this sort of thing. Conducted EMI simulations with PSIM, motor drive simulations, and then power supply design with PSIM are going to be the training material hosted next year. I will be hosting these sessions, and you will access those through the Altair One. There will be a sign up. There'll be more of a formal course. I'll provide you with labs to work with as we go through it. And it'll be a multi-day thing. So the 3-hour sessions will be an hour and a half over 2 days. So look for that to come next year. And to get to that, you'll have to sign up through the Altair One portal there. So these are all the sorts of things that are coming next year. And as we move to drive forward with more integration with what the Altair tool universe has. Eric, I think or Drew, out of things to talk about here. Or, I mean, I could talk more, but I might need more time.
No, I appreciate it, Albert. I think you saw the questions in the chat, right? I think you already covered.
Yeah, there was the one question about, oh, here, there was some more popped up. I was hiding. For the cable capacitance simulations, how do you obtain these inter-cable capacitance values? So this is what FICO generates. FICO generates off of your cable geometry. Let me just pull it up. So where is it here? So this is the file that FICO generates. Kind of move past a lot of the stuff at the top and get to the meat here. So this is the definition of each cable. So in my situation, it was 3, and let me just launch the solver here too. So just launching FICO. So this is what gets exported. So we see the inductance values and the capacitance values, and this is for segment 1. And it tells me how many segments I have. It's 15 to model this cable properly. And it gives me the inductance, the capacitance, and then it gives me the surface impedance, the transfer impedance, and the admittance. And all this data, I then took and I put it into PSIM. I built the equivalent circuit. So the way this is working right now is it's kind of manual, where I rebuilt the circuit. Where we're going is to do this off of a to do this off of S parameters. So we'll be able to do instead of having these distributed models, you'll be able to put an S parameter circuit in that'll drive it that way. But these capacitance values are calculated based on the proximity of that conductor to its neighbors, to the shield, to ground. So it's a full meshing calculation that does it. So yeah, so this is the beginnings of it. Home, that was wrong. FICO, EFS, post FICO. Did I launch pre-FICO already? edit FICO, post FICO, we want pre FICO. And then when it came to, so I was going to show the, oh, here. I'm not an expert on FICO yet, so there's a way of pulling up what the geometry looks like, but it's basically, it's a full solve. Display, mesh, result, animate. Yeah, there's all sorts of fun stuff you can do in here. I'm by no means, oh, CAD FICO is the one I wanted of this geometry. While that's loading, there's a ton of scripting examples. I didn't answer that directly. File, open examples in here, and script is right there. So look through all these examples, and there's a bunch of scripting things in there. Okay, here's CAD FICO. We just want the display options. Oh, geez. I'm not a cable guy. That's why I didn't open up FICO to begin with. Anyways, that's it. We've hit time. I do need to scoot to another call. If there's any other questions or comments, please let us know, and we're happy to answer them. Drew, over to you to wrap up.
Yeah, thanks so much for attending today, Albert. Great presentation. Appreciate you leading this. And yeah, if you guys have any other questions about anything, I'm throwing up my email in the chat. Anything PSIM related, I can elevate to Albert. So with that being said, I'm going to end today's webinar. If you want to come back and rewatch this, we'll be putting this on our YouTube. And thanks again for Albert for leading this webinar.
You're very welcome, guys. Yeah. Keep an eye out for all the trainings and other resources and other developments over the next couple of months. It's going to be exciting 6 months, I think, with regards